Hey class, many people have been asking me about this question number 3 on the workshop, so I thought I'd go ahead and make a short video. Now, a few people may have found that there's a shortcut equation known as the range equation to help with this problem, but what I want to do is kind of give you some hints as to how to do this without the range equation in case you don't know or understand it, and also as a result, this will help you with your pre-lab that's due on Wednesday since you're asked to derive the range equation. Due on Tuesday at the start of lab. So here's the situation, and it's kind of confusing because we're told that there's this cannon that shoots a projectile 275 meters, so that's the horizontal distance. This is what we call a range value when it's aimed at a 66-degree angle above the horizontal. Now here we're going to make the assumption that you're starting and ending at the same elevation or the same height. So if we call this, our zero location and the y-axis, what that means is that y initial would be 0 meters, and similarly y final would also be 0 meters. So you're ending and starting and ending at the same height. And keep in mind, that's the only time that the range equation is ever useful. Part of the reason I have not given you all the range equation before now is because people abuse it and misuse it all of the time. Do not do that. You can only use it when your starting and ending heights are the exact same. So it's rarely applicable, but when it is, it's really powerful. Okay, so we have the situation where our ending and starting heights are the same. Our initial location is 0 meters. Our final location in the x, I should say, is the range. I'll just call that r for now as a variable. And we're launching our projectile with some initial velocity that we don't know. But because velocity is a vector, we can actually take and break our initial velocity down into x and y components. So again, since the v initial is our hypotenuse, we can say that the hypotenuse multiplied by the cosine of the angle will give us our horizontal or x component, and the hypotenuse multiplied by the sine of the angle will give us the y component. And again, that's just making a triangle out of our initial velocity, or thinking about breaking our initial velocity into its vector components, thinking of it as having a piece in the x and a piece in the y direction. All right, so keep in mind that's a trick we're going to be doing a lot, but breaking things into the components, that only applies to the initial velocity. Don't try to use it for distances and other things because it doesn't work due to acceleration. Okay, so anyway, this is all fun and good. I'm getting some stuff set up. I'm identifying some of my variables, and I can keep going with these, identifying that our x acceleration is going to be 0 meters per second squared. Our y acceleration is going to be negative g. V final x is just going to be equal to v initial x. V final y, you might put a question mark. I would actually, because of symmetry, observe that it's just going to be equal but opposite to v initial. And then there's some time that we don't know. Okay, this is all fun and good, but this isn't even telling us how are we going to possibly answer this question. So in this question, we're asked to figure out the maximum possible range. So if I were to adjust the angle to something other than 66 degrees, how far would it go? And if I adjusted it to the perfect angle, what's the distance that it would go? Well, interesting, I don't know. But if I wanted to figure out the maximum range, one, I'd have to figure out the ideal angle. Many of us, I'm guessing, would be able to identify that the ideal angle for a maximum range is 45 degrees. And in fact, this problem can help you prove that that's true, and you are indeed correct. If you're starting and ending at the same height, 45 degrees would give you the maximum distance. But again, only if you're starting and ending at the same height. If you were to fast forward to problem 5 on the workshop, 45 degrees would not maximize the cricket's range because he's jumping off of that cliff. Okay, so then the question is, how far would this be traveling? What would the range be if you were to launch it at 45 degrees? Well, to know that, I need to know how fast the cannon shoots the ball. So what we're being told is that it travels a range of 275 meters at 66 degrees, and we need to use that information to find v initial. Then once we know the initial velocity of the cannon, then we can determine how far it would go if adjusted down to 45 degrees. Okay, so that's the process. What I will do now is start by using our initial situation here where we know the range and the angle and try to find the v initial. Once we have that, then we can find the new range. So how do you go about getting that initial velocity? Well, here's our setup, here's all our variables. And so I'm going to do everything in variable form. I know some of us don't like doing this, but it's helpful to practice it, all right? If you're somebody that doesn't like dealing with variables, you probably should be all the more urgently dealing with variables to get comfortable with it. Okay, so let's dive in. Let's look at the x direction. I think we've established that in projectile motion, the second kinematic equation is really the only one that's going to be helpful in the x direction. And that's because ax is 0, so this goes to 0. In this case, x initial is also 0, so all we're left with is x, our range, equals v initial x, which is v initial cosine theta, times t. Okay, so we have an equation. We know range and theta. We do not know v initial or time, two different unknowns. So I'm going to move on to the y direction and see if I can find something with the same two unknowns. So there's various ways to do this, but I found it most useful to use the second kinematic equation again, but now applying it to the y direction. So we're going to use the same equation and now plug in some of the things we know, and then zeros for the things that we know are zeros. So this is 0, this is 0. So we have 0 equals v initial y, which is v initial sine theta, times t, plus 1/2 acceleration, which is negative g, times t squared. So I can move the 1/2 gt squared to the other side, equals v initial sine theta times t. And now there's a t on both sides, so I can actually cancel out one of the t's. And then solving for t, I get t equals 2 v initial sine theta over g. So now I have two equations, both with the same two unknowns, t and v initial. So I'm going to actually substitute in to the other equation here in order to try to solve for v initial. So we get r equals v initial cosine theta times t, which is 2 v initial sine theta over g. So there's our substitution. Now, before we solve for v initial, I'm actually going to rewrite this one more time, well, two more times. R equals, I have v initial squared over g, and then I have 2 sine theta times cosine theta. Now, believe it or not, there's this weird trig identity that you may or may not remember from some time in your past, but there's a trig identity that says 2 times the sine of a given angle multiplied by the cosine of that same angle is always and exactly equal to sine of 2 times that angle. So in this case, if you had 2 times the sine of 66 multiplied by the cosine of 66, that would be exactly equal to the sine of 32, or 132, 66 times 2. So what that means then is if we plug this in, this substitution here, we get that the range is equal to the initial velocity squared, the total initial velocity, the hypotenuse value, divided by g, multiplied by the sine of 2 times the launch angle. So this is what's known as the range equation. It's actually on your equation sheet, and it's what's going to make this problem much easier to solve. And this derivation I just did is actually due as part of the pre-lab, so hopefully that helps you all. So to solve this then, what we're going to do is we're just going to go ahead and plug in 275 for r, 66 degrees for theta, and find v initial. Then you'll go back and do the same exact equation, solving for range now with that v initial that you find from the first part and the new angle of 45 degrees. I'm not going to do that piece for you. I want you to get the correct answer on your own, but I do want to take one more kind of side note here for you all. You may remember that the sine of anything, right, sine as a function varies, right? If I were to plug in 1 degree or 2 or 3 or 5 or 10 or 90 or 180 or 270, all these different values for theta are going to give me different values for sine. And sine, when you plug in the various different values, is a function that looks like this, a sine wave, hence the name. The sine wave will always vary between a maximum value of 1 and a minimum value of -1. So sine can never be more than 1 and never less than -1. So, why am I saying this? Well, if we look at our range equation, and if you're asked to confirm or figure out what is the maximum angle or what angle should give you the maximum range, I guess would be a better way to put that. If you have a fixed initial velocity, something that's predetermined by the strength of a cannon or how strong of an arm you have if you're trying to throw something, the range then, the only way to adjust your distance is by adjusting your angle. And what you're going to be doing is really adjusting this term. So for example, if you threw at a 0-degree angle, you'd be throwing it straight at the ground in front of you. Sine of 0 is 0, and so it wouldn't go anywhere. Similarly, if you plugged in 90 degrees, so you threw it straight up in the air, sine of 2 times 90, sine of 180 is also 0, and so it wouldn't go anywhere because it would go straight up and come right back straight down. And so since the maximum value of sine is 1, what we would do is we'd say, okay, to get the maximum angle, we would want to set the sine of 2 theta equal to 1. Well, if you do the inverse sine of both sides, you get 2 theta is equal to 90 degrees because sine is equal to 1 at 90 degrees. Solving for theta then, the max angle is 45 degrees. Something you probably already knew, but now we can prove it. So that's it for this video. Hope this helps. Let me know if you have any questions and have a box-worthy day. I'll see you all tomorrow.